All right, hello everybody. So attendance has noticeably dropped. I'm assuming, has everyone in here either like done lab 2 or haven't done lab 2? Oh, we got a thumbs up. Okay, so this is a group that did lab 2 and everyone else is still doing it. So people didn't believe me that if you like start on the weekend, you're probably screwed. So I guess they're kind of dealing with that now. So first order of business, lab 3, potentially longer than lab 2. So I added a petition. If you would like to have 3 weeks for it, go vote on it. So go open your Discord, hit the little check mark. Yeah.
Is it long in lab 2 as in like the coding is that long, then the debugging was like 10 hours? Or is it just like a coding itself is long?
So the coding's a little bit more than lab 2. You might find the debugging slightly easier or slightly harder depending on this lecture. So you probably want the 3 weeks for it. So go vote on that so I can actually change the syllabus and hopefully do that soon. Someone unvoted for it, so it needs like 30 more votes on the Discord. So make sure you have the check mark. That means your vote counts. And yeah, so that will also increase the wait for it, but it will make one lab be 1 week instead of 2 weeks, and it will be much, much shorter. So with that, let's dive into the next subject, threads, and then Thursday we'll have a bit more background. So this is what you're doing for lab 3. So as an aside, for those that haven't used threads before and don't know the terminology, so in computer science, we're a bit weird for normal people that can speak English properly, which is not myself. Concurrency and parallelism kind of mean the same things. If I do things concurrently, that's like kind of the same thing as doing things in parallel. But since we're computer people, we're weird, and they actually represent two different concepts in computing. So concurrency is being able to switch between two or more things, so you can get interrupted, make progress on something a little bit, switch to something else, make progress, switch to something else, go back and forth. And the goal there is to make progress on multiple things over a period of time. While parallelism is doing two or more things at the same time, and those two things can happen at the same time, meaning they're independent. And my goal for computing means I run as fast as possible. So if I have 8 cores, I want to run them in parallel. That means they're all doing something at the same time instant. So let's have a real life situation to make sure we understand what the difference is. So you have to bear with this like weird example. So you're sitting at a table for dinner. You have 4 options of what you can do. You can either eat your food, you can drink, you can talk using your mouth presumably, and you can gesture. And say you can gesture with one hand, any kind of gesture you can do. And the weird little caveat here is that you're so hungry that if you start eating, you just won't stop until you're finished, and that's so we can, discuss concurrency. So picking any of the 2 tasks, what can be done concurrently and what can be done in parallel. So, and also we're assuming we're like polite individuals. So if we take 2, like say talking and eating at the same time, that would be, you can't do them in parallel because you're not supposed to talk with your mouth full. And you also can't do those tasks in concurrently because you can't switch between them because of that weird little caveat that if you start eating, you can't stop. So between eating and talking, you can't do them in parallel and you can't do them concurrently. What about gesturing and drinking? So could I do those in parallel? Hands up. So we got a few parallel. Can I do them concurrently? Same set of hands? Yeah. So for both of those, I can do them in parallel or concurrently. I could what did I say? Drink and gesture? Yeah. So I could start drinking, gesture at the same time, with some skills, and I could do them at the same time in the same time instant, so I can do them in parallel. I could also decide to stop drinking whenever I want, switch to gesturing, go back and forth between them. What about eating and drinking? Can I do them in parallel? No, and can I do them concurrently? No, because of that dumb caveat where if I start eating, I can't stop. So if I start eating, I can't switch to drinking because, I don't know, I guess I haven't ate all day or something like that. And I also can't do them in parallel because I only have one mouth. That's kind of your limiting resource. So does that kind of make sense to everybody, the difference between them? So for an exhaustive list, here's where it is. So you can't eat and talk or drink at the same time, and you can't switch. So you would consider those tasks to be not parallel and not concurrent with each other. Yep.
If you're drinking a smoothie, does that count as you drinking at the same time?
Yeah, the question is if you're drinking a smoothie, does that count? And you're just drinking water. Like, yeah, not trying to overcomplicate things here. So this also, you can eat and gesture at the same time, but you can't switch because of that weird caveat. Sometimes you might encounter this in computing where if you start something, you can't resume it again. So you just have to do it until completion. And then you can drink and talk at the same time, and you could switch, but you can't do them in parallel. You can't do them at the same time because you have one mouth resource pretty much. But you could switch between them because you could use your mouth for different things. And then you can talk or drink and gesture at the same time, and you could switch. So those two tasks would be parallel and concurrent. So that's going to really matter once we have to, manage these types of things, and we'll see how this applies to us. But this is a good thing to keep in mind if you haven't seen threads yet. So what are threads? So we started in processes, and threads you can think of just as like a lighter weight processes, except by default, they're not completely independent, and they share memory. So there can be multiple threads within a process, and they can execute different pieces of code, maybe in parallel, maybe concurrently, and they're in the same address space. So any variable you can access in one, you can access in the other. But what is independent towards them is they have their own registers because they're supposed to represent virtual CPUs, and they have their own stack. But aside from that, that's the only part that's independent. They have their own stack, they have their own registers, which includes a program counter, which is what they're executing. But other than that, they share the same address space. So if you change a global variable in one thread, you see it in the other because they have the same virtual addresses, the same address space, they're all the same. So if you want things to be private per thread, you can do that, and that's something called TLS, or thread local storage. That is memory allocated specifically for one thread, not to be shared with others. But in this course, you'll probably never see that, only once you start using threads more hardcore. So you've been using threads already, even if you don't know that. So one process can have multiple threads. By default, a process has a single thread that starts executing things. So by default, a process just executes code in its own address space, and threads allow multiple executions in the same address space. So as a consequence of that, they're lighter weight, less expensive to create than processes, and by default, they share code, data, file descriptors, everything. They live within the same process. So knowing what we discussed about page tables, last week, why would creating a thread possibly be a lot faster than creating a process? So what's one thing I need to, oh, yep.
You don't have to copy the page table.
Yeah, I don't have to copy the page table. I don't have to potentially copy memory because they all share by default. They use the same page tables, so I don't have to copy anything. So that's one of the main reasons why it's going to be a lot faster. So I just have to basically allocate a set of registers and a stack, and I'm done. So why would I use threads, especially, they were a thing back when you only had a single CPU on a machine, so you can't do anything in parallel because you only have one physical core. But what they're good for is expressing concurrency, so you can have multiple different executions going on in your program at the same time that you switch back and forth between. So And if you switch fast enough, it actually looks like it's running in parallel, when realistically the operating system is just doing context switches fairly fast, and it just looks to our slow human brains like it's actually going in parallel. So why you would do this is it might be easier to program concurrently. For instance, if you know that, oh, well, I want to be juggling a bunch of different things at the same time. Some might be blocked on files or whatever, or slow. So one example would be like a web server. So this would be like the code in the core of any web server. It's just an infinite loop, and all it does is try and get a web request, like when you connect to a server, and then it will create a thread to process that request. So every request that comes in would have a new thread, which would keep track of that specific execution, and you can juggle like thousands and thousands of requests at the same time, do a little bit of work on one, switch to another, do a little bit of work on that, switch to another, do a little bit of work on that, and then finally finish. And that way you can handle multiple web requests. So here's like a breakdown. They're really similar to processes in the way we use them, aside from that default sharing memory thing. So with processes, remember we had like independent code, data, and heap between processes. But for threads, they're going to have shared code, shared data, and shared heap because they're not independent. They exist in the same address space. And each process has an independent execution. They're completely independent, while a thread lives within a process. So it is just one, essentially, thread of execution in a process. You can think of it as like a virtual machine within that process. The way that they're similar is, well, a process has its own stack and registers, and so does a thread. Or another way to think of it is just a process just has a single thread executing in it by default when you start it. So for a process, they're going to be expensive to create, and we have to context switch between them. That's going to be also more expensive because it would, as part of context switching, pretty much comes down to the page table. If we have to context switch, we have to change address spaces, which is going to take some more time than if we don't have to do that. And to create, it's going to be faster because, again, we don't have to copy the page tables. We don't have to potentially copy memory. So threads are a lot cheaper to create and a lot cheaper to context switch. For a thread, you don't have to change the address space. All you have to do is swap in some registers, and you're done. Now, for a process, what we've been covering in Lab 2 and what we know about processes is they're completely removed by the OS on exit after someone waits on them. And that whole process, everything associated with it is now gone, poof, doesn't exist anymore. While for a thread, if a thread exits within a process, the only thing that gets deallocated is its own stack and maybe some, whatever data you use to store its registers, and other than that, it's not that much data. And then as a consequence, when a process dies, all threads within it die as well. So if you have multiple threads within your process and your process dies, it brings everything down with it, which is one of the reasons why Firefox or Chrome tabs exist in different processes, because if they existed in threads, well, if there's a problem in one thread, brings down the whole process, which brings down your whole web browser, which means you're not going to have a good time. So in this course, we'll be using POSIX threads, and in Lab 3, you will be implementing your own threads as well. So these are like the default ones that will kind of that are going to be way more advanced than yours that we'll learn to use, and you'll implement a basic version of threads. So for Windows, there's like Win32 threads, but we're going to use POSIX threads. It's pretty much supported on everything. And to do that, it's another fun library. It's pthread.h. And when you compile, so on all these, they'll be given to you, but you have to link to that library. There's a pthread library. So all these threads have documentation of the man pages, which is nice and fun. Annoyingly, they don't quite follow the C system call wrapper convention. So they do they have a little bit of a different style when they return errors. So when we created processes, we forked, and then suddenly we had two processes. For pthreads, it's a bit different. So this is the API of a pthread create. So you have to give it a thread data structure, which has its own internal accounting. Then the second argument is some attributes you can set to set some options on how you want the thread to behave that we'll go into a little bit. And then the next argument is this weird void star start routine, void star. If you don't know C declarations, all that basically means is it takes a function that has one argument that is a pointer and returns a pointer back. So void star is just C's way of saying, it's just a pointer, I don't care what it is, you can figure it out. And then the last argument there is a pointer, and that will be passed whenever that start routine starts running, which might seem a bit weird. So creating threads is a bit different, so this is what it looks like. So instead of fork, again, we do pthread create. We give it the address of the thread data structure so it can initialize it with whatever it needs to. And then we'll just null for the attributes just means give me all the defaults. And then as the third argument, we say whatever we create this thread, we want it to start executing this run function. And then we will give it no argument. We'll just give it a default null. So at the point after pthread create, we now have two threads. Our main thread would continue executing as normally and want to just print in main. And then we have another thread that would start executing at the beginning of run, and it wants to have printf in run. So this is like if we had two processes, we don't know which one's going to execute first, and same with threads. So now we have two threads, we don't know which one's going to execute first. So if we go ahead and run this, go back. So here's the code again, and let's compile and run it. So it's compiled. So if I run it, it looks a bit weird because it just prints in main and then stops. So if I did this with a process, what am I missing? So if this was a process, am I a good parent? Hopefully not. Yeah, no, I should probably wait on it. So in this case, what's happening is, well, my parent is creates a child which could run printf, but the parent just printfs in main and then return 0, which is like an exit 0, and now that process is dead, so that other thread wouldn't execute, and I didn't wait on the thread I created. I wasn't a good parent. So there is an equivalent of that in pthreads. And the equivalent of wait for pthreads is annoyingly called join. So in join, you specify, there's no process IDs here, so you can't just wait on any one. You have to specifically wait for a thread. So if you do pthread join, you specifically wait on one thread, and here is an indirect pointer, so it's a pointer to a pointer. So that, whatever address you give it, it will write the pointer value returned by the run when it's eventually done. And that's a way to get information out of the thread. So by default, when we had a process, it just returned an int, like just a number when it was done. For threads, just to be a little bit more flexible, they always just return a pointer. So this is how to get the return pointer back. Yep.
So Professor, if we don't join the thread, then it becomes what, like an orphan thread?
Yeah, so
Or
you,
a zombie thread?
yeah, so you can kind of think of that. So if we go back to this, it kind of looks like an orphan thread, but because threads live within a process, there's really no concept of orphan threads because they're in your process. So instead of being an orphan thread and it getting reparented to whatever, when this process ends, it's dead.
It's just dead.
Yep, so it's part of the process. So if the process is gone, everything is gone. So there's there's a concept, we can find an equivalent of like zombie threads. So if we don't join a thread, we might have a zombie thread, but there's really no equivalent of orphan threads because they exist within your process. Okay, so here's our join. Like these, they return 0 on success and then directly give you an error number otherwise, and don't set error no. And the rule of this, like the rule of wait, is you should only call this on each thread, or in the case of wait, on each process, exactly once. If you call it multiple times, that's undefined behavior, as some of you have found out in lab 2. So don't do that. Same rule for threads. So if we wanted to, yep.
In the run function, what is the point of taking in void star?
So the question is in the run function, what's the point of taking in void star? So it's just a way to pass an argument to the thread function. So by default, to be as flexible as possible, it just takes a pointer. So if I wanted to pass a pointer to it, well, I could set this argument to whatever I want to appear as the first argument of run. And because everything's in the same address space, you can actually like pass a bunch of different information using a pointer. So everything would be accessible. Yep.
So if the parent process dies, does the thread die?
Yeah.
Oh.
Yeah, if the parent process dies, because threads live within a process, all the threads are now donezo. So if we go ahead and we do pthread join thread, and then null just says I don't care about the return value of it, like don't bother updating it, I don't care. So if we do this, we should now see always see main and in run printed whenever we execute this now. So because we don't know what order they might be in, well, we might get the order the other way around if we get unlucky, but we don't get unlucky. So it always prints in main and in run, but because we're kind of up to the scheduler, it could actually print in run and in main. We would just have to be like really, really unlucky, and remember that was due to the completely fair scheduler we talked about before, and the main process still has some time left to execute. So, any questions about that? Okay, and then I'll also have a little demo program. So I wrote to show that creating threads is way more expensive than creating processes. Well, I wrote another thing that just creates like 50,000 processes and then tells you how long it takes. So if I time this, whoops. So if I run this, this creates 50,000 processes. Oh, yep.
What does more expensive mean in this case?
So more expensive in this case means it will take more memory and it will take longer to run. So in this, if I just keep track of how long it takes to run, if I want to run 50,000 processes, well, in total time takes me like 14 seconds, while if I want to create 50,000 threads, well, hopefully that takes a lot less time. So it still takes a bit of time, but takes about like a third of the time. So that was like 4.8 seconds as opposed to 14 seconds. So just in time-wise, it's less expensive to create threads and processes, and that makes sense because they all live within the same address space. Okay. So next fun thing is, well, here's our example that waited properly. So we wouldn't have, we properly wait on our thread. There's no parent-child relationship really because everything lives within a process. So you can kind of think of whoever created it, but the pthread library doesn't care who created what thread at all. So there's no parent-child relationship in this case, but you can wait on any thread you want. But you still have that rule where you can only wait on a single thread. So now we joined, and at the point of the join, like same thing with the process, the thread's resources can be all cleaned up because it essentially read its status, and a thread's equivalent of status is reading the pointer value it returns at the end. So we joined it, we could read its return value, and we're good. So the library can go ahead, clean up all the resources associated with that thread now. So there's also a thread equivalent of exit. Thankfully, it's not named something different. It is called pthread exit, and that's how to return early, and it just takes a pointer value that you want to return. So, and there's also an equivalent of, main returning 0 and that eventually calling exit. Well, if that thread routine returns a pointer value, it eventually calls pthread exit. So same thing, yep.
When we learn about schedulers, task schedulers,
Yep.
how does it context switch between threads within the process?
So the question is, how does it context switch between threads within a process? So when you context switch processes, you swap all the registers and you swap the address space. For switching within threads within a process, when you context switch, you only have to swap the registers.
But is it say we split it to 10 milliseconds? So 10 milliseconds for some process. Is the thread also considered another task?
Yeah, so we'll get into it later. So the thing with threads are, because they live within processes, they can either be, the kernel can either know about them and then just do its normal scheduling thing, or the kernel cannot know about them and leave the scheduling up to you, and you decide. So the kernel will schedule processes. If the kernel knows about threads, it will also schedule those threads like processes. It might just be faster to switch within threads within the same process. And we'll go over next lecture more, getting into that in a bit more detail. Yep. Yeah, so if instead of pthread exit, I wrote exit 0, what's that going to do? So exit's a way to exit the process, right? So if I exit the process, everything's now dead. Yeah, so this is one fun thing you'll find that, hey, if one of your threads decides to call exit somewhere, well, that entire process is done and all your threads are now no longer running. So you have to be careful about doing that. So if you accidentally do exit instead of pthread exit, you might notice your whole process is now dead. Yeah, so, and again, you can think of that, oh, yep.
So this is used in exactly the same way as exit, right?
Yeah, except that it exits a thread instead of the whole process. So this is also, funnily enough, remember the name of our system call, like in lecture 2, was exit group instead of exit, and how people thought that was weird. Well, threads were introduced in the kernel much later in time, and exit would exit from a single thread, and then suddenly processes got multiple threads, so they came up with exit group, and exit group means all the threads within the process also exit. So that's why it's called exit group, because it kills everything. Okay. So by default, threads kind of behave like processes where you have to wait on them. You have to be a good parent. But with threads, there's something called detached threads, because sometimes you might just create a thread and you don't care about its return value. Well, with processes, you might not care about its return value, but the kernel doesn't really care about you that much. It makes sure you check it anyways. But with threads, you have a bit more leeway. So joinable threads are kind of like processes that you have to wait on them or join them, and then they release their resources. But for detached threads, they release their resources as soon as they're done terminating. As soon as they call pthread exit, all their resources get freed, and you don't have to worry about freeing them up. You don't have to worry about creating the equivalent of like a zombie thread. So if you don't join them, yep.
So then does a detached thread die when the parent process dies?
No, so a detached thread dies when it calls exit. So it's only that thread that dies, and it's just dead.
It's completely independent.
Yeah, So this, you can say a thread is detached by just calling pthread detached, and that will make that thread a detached thread instead of a joinable thread. If you don't give it any arguments, by default you get a joinable thread, which means you have to join it before it actually frees the resources. And then, like so many fun library functions, well, if you call pthread detached on an already detached thread, that's undefined behavior. It's allowed to do whatever and make it impossible for you to debug. So now we're faced with the same problem as before. So if we go back to that code where we wanted the other thread to run, we wanted to see it print in run. So we joined on it to make sure it was done before we eventually called exit and ended the process. Well, now if I make this a detached thread, I can't join it. So now I'm kind of in the same situation as before. So everyone understand why this probably every time I execute it just prints in main and nothing else. So any questions quickly about that? Okay, so why would probably it just print in main and then stop if I have a detached thread? Which hopefully it's the same reason. So I'll start off by having something that is executing main. It will create a thread that wants to execute run if it gets chosen to execute. And then I detach it, which means I don't have to join on it at all. It will free its resources whenever it's done. And then I printf in main, and then I'd have like an implicit return 0, which would exit 0, kill the process, and then that detached thread won't run. Oh, yep.
Sorry, if I missed this, like are regular threads joinable threads, and then we detach them, or?
Yeah, by default, when you do pthread create with just like a null here, you get a joinable thread. So this, by default, I get a joinable thread, and then I call pthread detach on it, and now it's a detached thread. So same reason, this just prints in main because that main thread just calls exit 0, kills the process, kills the thread. So, oh, yep.
If you put like a sleep before in main, would that allow the thread to execute?
Yeah, so if I put a sleep after in main?
Like before in main, or yeah.
Yeah, so if I put a sleep before or after, well, likely it's going to always print the other one depending on how big the sleep is because it'll have enough time, but you're still up to the kernel where it might not because you can't guarantee anything at that point. So I could guarantee it falls asleep for a second, but you can't guarantee the kernel will actually execute the other one in a second. So like 100% of the time that would print both, but it would also make it slow and it's not the proper fix. So yeah, you're just kind of arbitrarily slowing things down and hoping that it happens in time, which generally, unless you're working for a company, that's not a good idea. If you're working for a company, just write like a loop that loops a million times and makes things like really slow. And if you want to impress your boss, just like sometime a few months down the line, just delete it and things go faster. It's great. Fun work stuff. All right. Oh, yep.
Sorry, I still don't really get what the difference between a joinable and a detached thread is. I know they released the reasons sender this time, but
So detached thread, I can't call a join on it. So another thing that makes detached threads different than joinable threads is I can never get a return value out of them because I don't join them, so nothing can read them.
why would you want to create a detached thread?
So you'd want to create a detached thread. So sometimes you might create thousands and thousands of threads. And if you don't care about the return value at all, well, then you may as well make them detached threads because you don't have to remember to call join on every single one of them to release their resources. And otherwise, you might like slowly just run out of resources over time because nothing gets freed. So essentially, if you have joinable threads and you don't join them, they're like zombie threads, and they're going to waste some resources. So that's why you would have them, mostly just for convenience. Yep.
What's the difference between pthread exit and return?
So the question is, what's the difference between pthread exit and return from the thread function, right? Yeah, so that's the same question as what's the difference between returning from main and calling exit?
So you just don't have anything to return if you just call exit?
No, so if I do return from main with like a number, that eventually gets passed to exit, right? Like if I return 1 from main, that's the same as exit 1. So it's the same thing here. So if I return null, that's the same thing as calling pthread exit null. Or, yeah, yeah. By default, it'll call exit for you by returning from this function. So, yeah, everything in threads nicely has an analogy with processes, which is why it's done after. So, the reason this doesn't print both of them is because, well, one thread calls exit. So if I want, oh, is there another question? Yep.
Yeah, sorry. I know you can't kill join and detached thread, but can you call exit and kill it?
So the thread running run would be detached, and that calls pthread exit.
Okay, but like, could you kill it early with pthread exit?
Like I could do a pthread exit as the first line of here if I wanted to, but the problem here is my detached thread never executes.
Oh, so pthread exit is the thread killing itself. It's not
Yeah.
the process killing the thread. Okay.
Yeah, pthread exit is like the thread killing itself, just like exiting from a process is a process killing itself. So in this case, oh, yep.
Just to be sure, the reason it doesn't print in this case is because like we're exiting, which kills the process, kills the thread.
Yes. Yeah. In this case, before I saw both when I added the join, because I'm waiting for that other thread to continue, I could read its return value, but I don't. But I still have to wait for it to stop, so I'll also always see both prints. In this case, I don't have a wait anymore. So it's like the first problem where I didn't know which they can both execute, and just the way the scheduler works is I'll always probably see in main and not the other.
One last question.
Yep.
You mentioned earlier that we use exit group to kill all threads.
Yeah, so
Is it killing all the other threads, including itself, or is that the process calling?
yeah, so the exit group thing is like the system call, which is different than the exit call. So that's like more low-level stuff. So the C, confusingly enough, the C exit calls the system call exit group, which kills everything. And no one really uses a system call called exit anymore.
Okay.
Yeah.
So the process can't kill threads until unless it dies itself.
Yep. Yeah, so the only way to exit a thread is the thread calls exit on pthread exit on itself, and that thread is no more, or any thread running in the process calls exit, which ends the process, which ends everything. Yeah, so in this case, well, for a detached thread, we might want to wait for every single thread to finish executing before we finish. So how we do that is we can add our own pthread exit to the default kind of main thread that was executing main. So instead of hitting the implicit return 0, which would call exit, well, I can call pthread exit here, and that would stop execution of the default main thread. And as part of the behavior of the pthread library, well, it will wait for every single thread to exit before it exits the process. So in this case, I have two threads, an original thread that got created with my process that starts executing this code, and then the thread I create that is starting to execute run. And in this, likely what's going to happen is as soon as I create it, the kernel will keep on executing my main thread, which will detach the newly created thread, print in main, and then pthread exit itself, which will just kill the main thread. So it won't exit the process because there's still another thread that wants to run in main that wants to execute. So now, eventually, I'm going to execute or exit from my main thread, and then the kernel, if it wants to run my code, has no choice. It has to run that the other thread that wants to execute run. And if I execute this, it will always print in run. So let's go back. So detach fix. So now if I run it, no matter how many times I run it, I'm always going to see both get printed every single time. Yep.
So in this case, the main thread ends before the run thread?
Yeah, so in this case, the main thread pretty much always ends before the run thread starts executing. And that's just the way, that just has to do with the scheduler and how it works, because remember, you essentially get a time slice, and the main thread still has some time slice left over before it would try and context switch to the other one, which needs to set up and do some other stuff. So you're always going to, pretty much always going to see it. Yeah.
If you call exit in a thread, does that kill the whole process and all threads?
Yes. Yeah. Here, I'll show that. You have another question?
I was going to ask, so theoretically, like in the previous example, you could still get in run than in main?
Yeah, in both examples, I could get in run and in main, but without that explicit exit, I might just get in main and then nothing. Yep.
So, Professor, sorry, could you explain the pthread exit one last time? So does it, so it kills the main thread?
So
Does it kill the detached thread?
no, so pthread exit kills whatever thread executes that call. Just like when you exit, it kills whatever process that is. Like I can't kill another process without like sending a kill or something to it.
But is the process killed?
No.
Okay.
So in this case, with detached threads, the way the pthread library works is, well, it will only exit your process if all the threads are done, if all your threads call pthread exit. So if I did do something like, say I did this, well, I would have to get lucky, but potentially I would never see in main, because what could happen is main creates the thread that wants to start running run, and the main thread would want to run this afterwards and printf in main. But if the scheduler decides to immediately switch, well, the other thread would just call exit, and then the process is dead, so all the threads are dead, everything's dead. Yep.
So I think earlier you said in the void run for return null, it's equivalent to
Yep.
thread exit null. So in your main, could you have replaced the pthread exit with just a return null, like the main one? Could you do that backwards?
So in this one,
Yeah. Could you have,
like that,
yeah, instead of, would that do the same thing?
so this would not do the same thing because it's not like a function pthread knows about. It's your default C main, and you don't change the C main. So the C main still has the same rules that if you exit from that, that's the same as calling exit. So it's the same rules, like this is exit 1, same as, yep.
Just to confirm, the previous example is the detached error.c, right?
Yeah, the previous example without the exit, it's just the detach error. Yeah.
Theoretically, it should be able to print in main and in run both at least once, but it doesn't because we return, right?
Yeah. So in this case, it could print them both if we get lucky. But what happens most of the time is the main thread creates it, keeps on executing, printfs in main, and then returns 0, which is again the same as exit 0. And then the process is done and the other thread doesn't execute. Yep.
So I have a following question. If you repeatedly run this file, there is a very rare chance that instead of printing in run just once, it prints it twice. Why does that occur?
So question, if I run this, it prints in run twice?
Yeah, so if you repeatedly run it, I'm having like occurrences where I see in main and then the in run is printed twice.
Okay,
Does that occur?
okay, I'll have to look at that later. So I see 2 in runs, so I haven't seen that yet, but we'll see. I'll try and look at that later. Okay, yep.
Sorry, is there any
So remember that by default, like processes, when you exit them, they just want a number. For pthreads, they want a pointer.
Okay, so like if I return a number, it means I just exist the whole process. But if I'm gonna return null or some other stuff, I will just exist that a single thread.
No, so you can only, so the only default returning a number and exiting the process is only returning from main. And if you want to, exit a thread, well, you have to return from that thread function that's executed. But no other functions, like they don't magically know that, hey, you returned a pointer, so you want to exit the thread. It's only the function you specify.
Okay, so if I have an exist of 0 in a wrong function, I will just basically exist the process. But if I have a return null in that function instead, I'm just gonna only exist that whole thread.
No, so.
In both cases, I just exist the thread.
So if you just return a number here, it doesn't magically know that that's supposed to represent a process. That would just still return a pointer and then force a 1 into it, which would be meaningless. So the only way it matters is it's the function specified by pthread create, and it's a run, and it's supposed to return a pointer. So whatever that function returns will be the same as pthread exit, and only that function.
Okay, so every time you are only gonna exist the process is when you return a number or return something from the main function.
So yeah, the only default exit of the process is returning from main, like it has been forever. And it's like you can make another function that returns an int. It doesn't exit your process, right? Yeah.
If you try to do something else after pthread exit null, will it just not execute?
Yeah. So if I do like pthread. If I do something like this, I would never see the printf of cool because the thread would have been dead by then. So that's essentially dead code. So you can write whatever. Yeah, okay, so I answered the parent thing too. Okay, so quick bit of fun. So there's some attributes you can play with pthreads. We'll probably always just use the default, but this might help to give you an idea of everything has a size limit and everything, everything has a size limit. So you can see how big of a stack it will allocate for you, and you can change it if you want, or just accept the default. So if you write code like this, it's like a weird C way of actually accessing stuff that you should probably get used to. And if you do this, you'll see that the stack size is just 8 megabytes. So whenever you create a new thread, you get an 8 megabyte stack associated with it, which is private to that thread. And you could also use this attributes if you want. Instead of calling pthread detach, well, you can create one of those attribute objects, and then you could, set pthread create joinable on it or create detached on it. And then you don't have to have the separate pthread create and then pthread detach. You could just give it as an argument in attributes. But pthread detach is so common that they just made a nice little helper function, so you can call that instead of dealing with all of this crap. So if we compare, well, we can look at this real quick. Creating multiple threads as opposed to creating multiple forks. So let's go ahead and see that. So here's the example we'll end on. So in main, by default, again, you can think of there's only one thread running the main. Typically, you just call it the main thread. And what it's going to do is, instead of that forking stuff that we saw before, which is actually somewhat hard to read, this will go into this for loop 4 times and create a new thread, each with an ID. And then at the end, we will pthread exit, so we can make sure that all the other threads actually exit. So in here, we're going to actually pass an argument to a thread, and because everything shares the same memory space, we can just malloc stuff. So our main thread would call this, malloc an int, which gives us back a pointer, and we will write the current ID to and dereference that pointer and write the current ID to that, so that and then pass that pointer to the thread, so only that thread can access that pointer. And we create a thread data structure here. We create a new thread, give it some default attributes. We tell it to start executing run, and we will set, we'll give it that pointer argument, which is whatever malloc returned. Yep.
Sorry, why do we have to malloc an int? I thought usually you don't have to do that.
Sorry?
Why do you have to malloc an int?
So I need to malloc on an int here because I need to pass it a pointer, and I need some fresh memory to pass to it. So we can go over this, what would happen if you didn't do that, and it's bad. So we can do that as an extra thing tomorrow. Here, I'll finish it quick, and then tomorrow we can catch up and see all the bad things that happen with this. So in run, it dereferences that int to get the ID back out of it, freeze it because we don't need it anymore, and then it will print the thread ID and do this 10 times. So if we execute this quick before we go, we see that it's kind of like the multiple process example where we'll see, IDs, see each thread print 1, 2, 3, 4, 5 all the way to 9, or 0 all the way to 9, but the order between the threads will be all different. So here we got 1, 2, 4, 3, 1, 2, 4, 3, and for extra fun, look at that code and see all the bad things that we've done, because we did a lot of bad things there. So just remember, pulling for you, we're on this together, and go vote on the thing so I can post the lab with a later due date. All right.